I trust that you know how to solve the ODE at the bottom of page 1. So you could probably skip this video, but in case you want this video, here's some ideas on how to solve that ODE that we learned last semester. Here is the ODE x double prime plus k squared x equals 0. Notice I took the lambda and I put k squared instead of lambda, and I put everything on the same side of the equation and multiplied by the negative to make sure that everything is positive. And so this is a nice linear second order homogeneous ODE. We learned this in chapter 3 of the textbook last semester. It was on test 2. There's a characteristic equation. If we suppose the solution is some e to the rx and we plug that into there, we would simplify the whole thing into this characteristic equation. R squared plus k squared equals 0. There would be two chain rules there. So with e to the rx, two r's would come outside, and e to the x would be everywhere that would cancel. So this is the characteristic equation. You probably remember how to write the characteristic equation. And so when you solve that, you get plus or minus ik. Now, i's are fun little things in math, these imaginary numbers. Here I've put on this whiteboard for you to see, and you can copy it into your notes if you want. This is Euler's identity. E to the I theta is cosine of theta plus I sine theta. We learned that last semester. We saw that last semester. So if you change the I to a negative I, that's like a negative theta instead of a theta. Notice cosine does not change because cosine is an even function. Sine does change. Sine is an odd function, so the minus sign comes out. If you recombine these or rearrange these, here these are solved for, e to the I theta and e to the minus I theta. If you recombine these and solve for cosine, you see that cosine is the average of the two e to the ikx and the e to the minus ikx. It would be the average. You'd get that it's half of one plus half of the other. That's an interesting little formula here that's good to know. Sine of kx is kind of the same thing, except it's a minus instead of a plus. And we also have to put an I out there to cancel the i's that show up in Euler's identities. And so in differential equations class, we learned to take these characteristic values, or also sometimes called eigenvalues, and we put them into the exponential function. So we have e to the ikx and e to the minus ikx. So this is the solution to this equation, but this is not the only way to write this solution, because remember the a and the b are arbitrary constants. This is just a linear combination of these two basis functions, and so any other basis could describe the same space. And in fact, since these two things, sine and cosine, are also linear combinations of these, sine and cosine make a different basis for the same linear space, or to describe all the linear combinations that make up all these solutions. And notice this is a nicer basis because it does not have I in it. So on the handout, it just says the solutions to this equation are a sine x plus b cosine x. This is where sine and cosine come from, in case you didn't remember from last semester. I trust that you do remember from just last chapter, from chapter 5, how to use the homogeneous Dirichlet boundary conditions to figure out that the constant b, the arbitrary constant b, has to be 0, and also that the eigenvalues have to be n squared pi squared over L squared. The k equals n pi over L, I trust you remember from last chapter, right before I left for this to have the baby that I'm sure I'm enjoying right now.